So how do we calculate the change in entropy of surroundings, right? That's the hard part. We can imagine that for our system, we can keep track of everything that's going on and actually count the states in some way. But how do we count all the states of the universe? We don't know what's there. But it turns out there are, it actually ends up being relatively easy to calculate the entropy of the surroundings. So first, and I'm not going to prove it, this is a hand-waving explanation. And there's better proofs, but you need multivariate calculus to do that. So our first is our assumption is that the change in entropy of surroundings is proportional to minus the change in enthalpy of the system. So because giving off heat to the surrounding raises the temperature of the outside and makes everything jiggle around more. So if the system releases heat, it will increase the entropy of the surroundings. Our second point is that the change in entropy of the surroundings is proportional to 1 over T. Now, it's not immediately obvious why this is here. It's exactly 1 over T. But just to get a sense of roughly what's going on is at higher temperatures, the total entropy is already higher of the surroundings, right? Because, if you're at nearly at absolute zero outside, there's very little entropy. If you're at high temperatures, then, of course, there's a lot of entropy in the surroundings. But you're putting out the same amount of heat. So the same amount of heat has less of an effect on the entropy of the surroundings when the entropy of surroundings is larger. If it's at absolute zero, then a certain amount of heat could be like could create like 10 times the total entropy. Whereas if it's it's very hot, then you're just changing it by some minor fraction of a percent, and so that that difference ends up resulting in a constant of proportionality, that the change in entropy of the surroundings is proportional to 1 over the temperature. Okay, so putting these together, this would say that the change of the entropy of the surroundings is equal to minus the change of the enthalpy of the system divided by T. And this is an extremely powerful equation. Again, much better proofs in physical chemistry, but require a bunch of multivariate calculus to show. It's an incredibly important identity because it allows us to keep track of the behavior of the system, the surroundings as a whole, based on just the enthalpy of the system. That's really quite amazing. Is we just measure what's going on in the reaction flask, and it tells us everything else that's happening in the surroundings. So this is really cool. Instead of having to look for spontaneity by looking at the entire universe as a whole, we can just pay attention to what's going on in our flask and see how much heat it transfers to the outside. So we can come up with a variable that describes all of this, that describes the system plus the surroundings, the entropy of the system plus surroundings in terms of things that are only the system. So what this is called the Gibbs free energy, a system quantity. So we only have to keep track of a reaction that measures the entropy of the universe, the system plus surroundings. So what we do, we know the entropy of the universe is the entropy of the change in entropy of the universe in a process is the change of entropy in the surroundings plus the change in entropy of the system. So we replace that change in entropy of the surroundings with minus the change in entropy of the system divided by T plus system. And now we notice everything on this side is system labeled. And so we multiply both sides by minus T. So now we've got minus T change in entropy of the universe is equal to, now we have a relatively simple formula, delta H system minus delta T delta S system, and we call that the Gibbs free energy of the system. Free energy is essentially a measure of the useful work you can get out of the system. And we'll explore that a little more as we go through. That's the free energy. That's our quantity. It's a system quantity that is equal to minus T delta S universe. So if the change in free energy of the system is less than 0, that's the same thing as the entropy of the universe being greater than 0, which means it's spontaneous. Free energy less than 0 means it's spontaneous. Free energy equals 0 means it's at equilibrium, which means the change in entropy of the universe is 0. And if the change in free energy is greater than 0, it's non-spontaneous, which means it's a process that must have decreased the entropy of the universe. Okay, so we can measure the universe in terms of just keeping